Hi viewers, welcome back to the course. This particular video falls to a series of videos in which we have looked at questions and solutions which were asked in GATE from the topic mechanical vibration. So here we have a problem. A mass M is attached to a spring and it is subjected to a harmonic excitation force. Everything is provided in the figure. They are asking what is the value of M, what is the value of the mass, and for obtaining that they have given us a few useful information. So pause the video, try to solve the problem on your own. If you are not able to do that, come back and see rest of the video. The useful input from their side is the amplitude of the steady state motion is given as 50 mm, 50 mm. So to understand the theory behind this problem, I will just briefly discuss that. Here you have a single degree of damped system and it is undergoing a harmonic excitation as shown over here. Then in the earlier video I have established that the response will look like something like this: x of t equal to modulus of x of I omega e raised I omega t minus 5, where this is the phase difference and this is the amplitude of the vibration. We are interested in the amplitude of the response because in the question it is provided as 50 mm, and amplitude of the response is related to this is the static deflection, and it is related to the frequency ratio and to the damping ratio, like this, through this particular formula. R is the frequency ratio, which is the ratio of forcing frequency to the natural frequency, and zeta is the damping ratio. So the first question, what is the value of zeta for this particular problem? It is 0 because this problem there is no damping. So the equation boils down to this. This is the amplitude of the response is related to the static deflection, like this. So let me just put everything, let me just bring all the information that was provided as part of the input. So here we have, let's say here we have the stiffness, here we have the excitation force. So just bringing in all the inputs, I have the static deflection computed like this. Again, see, I always keep track of my units, so I'm converting the static deflection into mm for the sake of simplicity. Then plugging back to the equation for the amplitude of steady state response, I am reaching here. So there is only one unknown, r square. R square is the ratio of omega by omega n. So from that, only unknown is omega n, because we know the excitation frequency, which is 100 because the forcing function is given as 100 cos of 100 t newtons. Okay, so after performing all these manipulations, we arrive at an expression for r like this: r equal to 1 by 3. Then we substitute for r is nothing but the frequency ratio omega by omega n. Omega is known, 100, omega n is unknown. So I substitute for omega n in terms of the stiffness and the mass of the system, like here. Then stiffness of the system is provided, which is 3000 Newton per meter. All other quantities are known, so the only unknown in this particular expression is m. I do all the mathematical simplification and I turn this particular mathematical crank, and I finally arrive at an expression for m, as shown over here, which is 10 kg. But suddenly you look at the options and you can't see the option 10 kg. What happened? Where did we go wrong? So pause this video at this point of time and recap all the steps what we did and come back where we went wrong. I hope you found out where we went wrong. Where we went wrong is right here. See this particular expression over here. See, this particular expression should be viewed with extreme care, because here there is a square term over here. So there are two possibilities here. Once you substitute all these things, this 50 equal to 100 by 3 divided by 1 minus r square is one particular possibility. This is a fourth order equation and it has multiple roots. This is one possibility, and the other possibility is like this, where, as you can closely observe here, this 50 mm divided by 50 mm is equal to 100 by 3, which is the static deflection, divided by minus 1 minus r square. This is also true because in the denominator, let's say if that whole term is minus of 1 minus r square, then you're taking the square root of this whole thing and then only you're taking the square root. So eventually both, let's say this is the case 2 and let's say case 1, both of this, let's say in case 1 we have just 1 minus r square whole root 1 minus r square whole square root. Both these cases the end result will be same. So this is another value of r square which will satisfy all the conditions for this particular problem. So this is something which I missed out in the initial phase of the problem. I intentionally did it so that you will have an idea, or you will treat this kind of problems with a much more care. Okay, then repeating the same set of exercise for this particular solution or this particular case, we will get r square equal to 5 by 3, substituting for r square, omega square divided by omega n whole square. Simple maths, then you will finally end up with a value of m which is equal to 0.5 kg. That's all. So whenever you work with equation for magnification factor, always remember that there is a square root of square term. So there are two possibilities with which the equation and all the conditions in the problem will be satisfied. So always pay attention to those details. Thanks for watching.